In this video, we're going to go over problems that you might notice in your practicals and how to overcome them, okay? So if you're doing AQA, paper 3, section A is riddled with loads of practicals, and you have to think, I'm a theoretical physicist, okay? That's what we're normally doing in all of our papers, but in these questions, we're practical, okay? We're experimental physicists. You have to imagine you're in the room with this practical and you're thinking about what could go wrong, right? You're not trying to do really hard physics, math, and physics problems. You're actually trying to break it down more. You're trying to think, if I'm in this room, what could go wrong, okay? And the same thing for Edexcel or OCRA, but instead of it being on one paper, it can be spread out throughout your other papers, okay? So, practicals. First thing you need to be aware of, what is a systematic error? The way I remember it, a systematic error is clearly something to do with a system. A system is something to do with equipment, okay? System is something to do with equipment. Whereas a random error is something to do with a human, okay? So problem with equipment or versus with a human, okay? So what could be problems with equipment? First thing is, think about your scales, right? Everyone knows if I'm going to use scales, I need to make sure it's going to say 0 before I get on it, okay? And I'm going to try to weigh myself in scales before it says 0 because I'm going to get the right read it, okay? So let's say the scales read 0.1 before I get on top. And when I get on top of it, it says maybe 78.2. Okay, so now I'm trying to figure out what really is my reading. Okay, so it says 0.1 before I got on, it says 70.2 when I got it. So really my real value or my true value of my mass is actually 70.1. Okay, whereas here, if I did make sure that it said 0 to begin with and I got on it, it would just say 70.1 after, right? It went up by 78.1. This one went up by 70.1. Okay, so again, an example of a systematic error is called a zero error, right? So the problem is it didn't say 0 when you began. So if it didn't say 0 when you began, what you should do is they want to calibrate your equipment. To calibrate the equipment means you just want to reset it. You want to make sure it says 0 before we begin with. So if it's your scales, there's a little dial in the back. You can make sure that it says 0 before we begin with, or sometimes just tapping your foot, make sure it says 0, okay? Places that you'll see it other than the scales, again, if I'm using a stopwatch, I need to make sure it says 0 before I'm using it. If I'm using a Geiger tube or a GM tube, say I'm measuring radiation, I want to make sure that I first have to make sure that I record the background count rate. Okay, so this one's not so much that it's going to say 0 beforehand, because it shouldn't really say 0 beforehand, right? So basically, it should say 0 as soon as we hit, before I hit start, it should say 0, right? That's the first thing, yeah. So we do want to make sure it says 0, like right at the very beginning, before I hit start. But we know even if our source isn't in the room, we should still get a reading, okay? So let's say I've got a source of radiation. Let's say it is a source of gamma radiation. I know even when that gamma radiation is not in the room, I'm still going to get a reading on my tube, okay? And that could be another type of systematic error. The problem could be you took your source and put it in the room and you recorded the reading on the Geiger tube, let's say you record it for 20 minutes. Let's say after 20 minutes, the count rate said 500, okay? You think then that's all because of my gamma, but that's not actually right. That would be a systematic error because what you forgot is that there's some background radiation. So what that means is all of your data is going to be slightly off. It's going to be slightly too high. Because let's say the background radiation is 50. So the true value isn't 500. The true value of the radiation after 20 minutes due to the gamma source is actually 450. So all of your values will be offset by the same amount. Okay, so a systematic error is a problem in the equipment. All of our values are going to be offset by the same amount. So for this one, what we should have done is we should take the source out of the room. We should record the background radiation with no source in the room for say 20 minutes. Record what that value of background radiation is, and then we put our source in the room. We make sure that we get the corrected count rate. So remember what the corrected count rate is that whatever the count rate says after the new time, so we go for another 20 minutes, we subtract the background count rate from it to get the corrected count rate, okay? The count rate just because of our source. Okay, random errors then are problems with the human, okay? So a big one is due to your reaction time. Okay, so let's say we're doing the required practical where I want to measure the value of G, okay, acceleration due to free fall. Let's say I have some ball, and let's say there's an electromagnet here holding the ball up. If I turn the electromagnet off and the ball drops, let's say I want to record the time that it's going to take to drop to hit the ground. If I use a stopwatch, my reaction time is going to be a really high percentage of this value. okay? Because a human reaction time is normally anywhere between like 0.2 to 0.9 seconds, right? So it's going to be a big value of the time it takes a ball to drop. So we shouldn't use a timer because of human reaction time. We should use things like light gates, okay? So to solve it, we use things like data loggers. And the reason we use data loggers, again, is to avoid that human error. And also, we can get a higher rate of results, okay? It can take values a lot quicker. It can hit start and stop a lot quicker, basically. Okay, other things with human error is, let's say I want to record the volume. Okay, so let's say I'm doing my density practical, okay? And I'm recording the volume of liquid. And let's say I've got my numbers here at the side. Okay, one problem is a lot of people want to read from here. So let's say that says 100 up here. But what really you should be doing is you should be reading from the bottom of the meniscus. So it's actually the number 90, okay? So it's called the meniscus. Okay, so you probably see this in your bottles. So if you have a bottle of water, or you get a bottle of Coke or a bottle of Fanta, if you look at the water right at the top, that's the easiest place to see it. You can see there's a dip in the liquid, okay? And the dip in the liquid, it's called the meniscus where the dip is. And you always want to read the volume from the bottom of that meniscus. Another problem is parallax error. So a problem with parallax error is that instead of you reading from eye level, so again, let's say I'm trying to read the volume of my liquid. Instead of me getting down and trying to read it from eye level, I might stand up tall and try to read it down. But again, if I'm standing up here, that's my eye. If I'm standing up here reading it down, I'm going to get a lower value than what it actually is. Or let's say it's up high and I'm trying to read it up high. Again, let's say I'm down here trying to read it. I might get a higher value than what it actually is. So to avoid parallax error, what we should do is we always need to read it from eye level, right? So when you're doing these practicals, you need to make sure you go down and you read it from eye level, or it's just something we write about in your experiment. Okay, next one. Accuracy versus precision. Okay, if something is accurate, what that means, your value is close to the true value. That I can't spell true. If something is accurate, it's close to the true value, okay? So let's do my mass again. Let's say my mass is 70.2 kilograms. Let's say the first time I took the recording, I got 70.1. The second time I took the recording, I got 69.0. The third time I did the recording, I got 78.2. Okay, you can see that if I take the average here, if I take the mean of those results, I roughly end up with a value that's equal to 70.2. Okay, so if I take the mean again of these results, so again, what we mean is we add them together and divide by 3. I'm going to get a value that's really close to 70.2. So it's accurate. However, this is not very precise. So it is accurate, but it's not precise. What precision means is that all of your values are close together. Okay, this is not precise because my readings have fluctuated quite a lot. If I wanted to get accurate and precise readings, I should have got something like 70.1, 70.0, 70.2, 70.3. You see how this is both accurate because if I take the mean of all those values, I get a number that's exactly or basically exactly like my true value, but they're also really precise because all the values are really close together. Okay. One thing else that you need to know about here is a way to reduce random errors. So a way to reduce random errors is always to repeat it, okay? So that's why I want to repeat the experiment, because let's say I did something wrong, like recording the time. If I do the experiment loads and loads of times, 1, 2, 3, 4, 5 times, and I get loads of different values for my time, it's really easy for me to spot if I made a mistake. So let's say I'm recording the time for this ball to drop. The first time I get 0.2 seconds. The next time I get 0.3 seconds. Then I get 0.1 seconds. And then the next time I get 5 seconds, 5.0 seconds. Clearly, if I looked at this, something is clearly wrong with result 4. That's called my anomalous result. So then that was easy to spot that I made a mistake there, a human error, a random error. So I just ignore that value or I just repeat it again.